So hello everyone, today we will start with the session 7 of atomic structure, right. So this is the basic overview of session 7 of atomic structure, discovery of fundamental particles, neutron, proton and electrons, and we consider the atomic models, that is the Thomson, Rutherford and the Bohr's. Bohr's model we have discussed to some extent, and the spectral studies have also been discussed. Uncertainty principle, photoelectric effect and the electronic configuration we will be discussing in the upcoming session. So this session will consist of basically the drawbacks of the Bohr's model of an atom. Okay. So let us consider first this question that if the energy of electron in first orbit of helium plus is T, then what is the energy of electron in the fourth orbit of lithium 2 plus, right. So first we will write down that energy equals to what? Minus 13.6 Z square divided by what? N square. So first we will take the energy for helium plus. This will become equal to minus 13.6 into Z for helium is what? 2. So 2 square becomes 4. And the first orbit means that N equals to 1. So 1 square becomes 1. So it is saying that energy is T. So T becomes equal to what? Minus 13.6 into 4, right. Now coming on to the energy for lithium 2 plus, we can write it as minus 13.6 Z square divided by N square. So this becomes minus 13.6. Z is what for lithium 3, that is 9, and N is what for lithium 4th. Right, so 4 square will become what? 16. Now you have to calculate the energy of lithium 2 plus in terms of T. So you can replace the common term, that is minus 13.6 here with T. So minus 13.6 will have a value of T by 4. Minus 13.6 will be having a value of T by 4, right. So E will be becoming equal to T by 4 into 16 into 9. That means the answer that you will obtain for this particular question is what? 90 by 64. Okay. Now moving on to the Bohr's model explanation for spectral studies, right. So here if you see Bohr explained that the energy will be released when the electron is coming from a higher orbit to a lower orbit, right. From a higher orbit to a lower orbit, energy will be released, and energy will be absorbed when the electron will move from a lower orbit to a higher orbit, right. So now energy of the electron can be written as minus 13.6 Z square by N square. This was the formula given by the Bohr's. Now what will happen is that we want to calculate the energy difference between the two levels. Let us say that an electron is moving from energy level 2, that is N equals to 2, from energy level 1, that is to N equals to 1. So what is the energy of energy level 2 here? Minus 13.6 Z square divided by N2 square, right. And what is the energy of first orbit? That is minus 13.6 Z square upon N1 square. Now we want to find out the difference between the energies, that energy levels basically, that is N equals to 2 and N equals to 1, that is delta E. So delta E will be equal to what? E2 minus so delta E will be equal to what? E2 minus E1. So this will become minus 13.6 Z square upon N2 square minus of minus 13.6 Z square upon N1 square, right. Now this will become minus 13.6 Z square upon N2 square, minus and minus will become plus 13.6 Z square upon N1 square. If we take 13.6 as common, basically 13.6 Z square as common, we are left with 1 upon N1 square minus 1 upon N2 square. right. So this is what basically equal to delta E. Now we know that delta E is equal to h nu, right, and nu equals to what? C by lambda. Nu is the frequency, C is the speed, and lambda is the wavelength. So it becomes equal to delta E equals to hc by lambda, right. Now we will replace the term delta E by hc by lambda. Let us see what does it give. hc by lambda will give 13.6 z square into 1 upon n1 square minus 1 upon n2 square, right. Here the convention is that n2 is greater than n1. Okay, so now hc can be placed in denominator here. So 1 by lambda will be given as 13.6 divided by hc z square 1 upon n1 square minus 1 upon n2 square, right. Now if you calculate this particular thing, that is, put the value of Planck's constant as 6.62 into 10 raised to the power minus 34 and C as 3 into 10 raised to the power meter per second, and this you can convert it into joule also, right. So you are getting this particular value as what? This particular value is the value of the Rydberg constant, the constant that was given by Rydberg, right. So Rydberg just gave an equation. Bohr was basically able to derive the mathematical explanation of that particular equation. He found out that this particular value is coming approximately equal to the constant that was given by Rydberg. So coming on to the equation that was given by Rydberg, it was that 1 by lambda equals to Rydberg constant into 1 upon n1 square minus 1 upon n2 square, right. Now here the difference is what? Z square basically, right. Z square term is not involved in Rydberg equation. Why is it so? Because he proposed this particular equation for the spectra of hydrogen, and hydrogen Z equals to 1. For hydrogen Z equals to 1. Therefore, if we substitute 1 in this particular equation, both the equations are matching. This one was proposed by Bohr and this one was proposed by Rydberg, right. So both of them were coming on to the same formula. The only difference was that Rydberg gave a equation without the explanation, while Bohr was able to explain the concept fully, that how that particular equation can be derived. Okay, so yeah, value of Rydberg constant is what? 1.09 into 10 raised to the power 7 meter inverse. This you have to remember. This is very important. This value you have to remember. This will not be given in the exam itself. Okay, so now using this particular formula, that is 1 upon lambda or nu bar, that is the wave number, that is the reciprocal of the wavelength, is given as 13.6 or basically the Rydberg constant into 1 upon n1 square minus 1 upon n2 square, where n2 will be greater than n1, right. And this is for what? This is for the hydrogen atom, right. If you are studying the spectra for other atoms, right, which are having another Z value, then you have to keep Z square also here. For hydrogen, Z is 1, therefore the equation is reduced to RH into 1 upon n1 square minus 1 upon n2 square. While for other species, you can take it as RH into Z square, where RH is having a value of what? 1.09 into 10 raised to the power 7 meter inverse, right. So in Lyman series, if you see that n1 is 1 and n2 can be 2, 3, 4, 5, 6, 7. Balmer, n1 is 2 and n2 can be 3, 4, 5, 6, 7. Bracket, Paschen series, n1 is 3 and then n2 can be 4, 5, 6, 7. For bracket series, n1 can be 4 and then n2 can be 5, 6, 7, 8. And for Fund series, n1 is what? 5 and n2 can be 6, 7, 8, 9, 10 respectively. Okay. So this is how Bohr was able to explain the hydrogen spectra Okay, basically what? The emission spectra. Here we are studying what? The emission spectra. That is, the energy is being released. That is, the electron is coming from a higher energy state to a lower energy state. Okay. Now the question arises that what is the number of possible spectral lines that can be emitted when an electron de-excites from third orbit to the first orbit. So a general formula to find out the number of spectral lines is that n equals to n2 minus n1, n equals to n2 minus n1 into n2 minus n1 plus 1 divided by 2. Right. So here you are giving where obviously N2 is greater than N1. So here you are given that N2 is 3 and N1 is what? 1. So eventually you can calculate out the number of spectral lines. So to find out the number of spectral lines, N2 can be 3 and N1 can be 1. So this will be 3 minus 1 into 3 minus 1 plus 1 divided by 2. So 3 minus 1 will be 2 into 3, that will be divided by 2. So the answer will come out to be 3. So the number of spectral lines that are possible that can be emitted when an electron de-excites from third orbit to the first orbit is 3. Now coming on to the question, what is wavelength of the radiation emitted when electron is making a transition from n equals to 5 to n equals to 2? Now just we have to apply the Rydberg formula, that is 1 upon lambda RH into z square 1 upon n1 square minus 1 upon n2 square, where n2 is greater than n1, right? So here you will get 1 upon lambda as RH is what? 1.09 into 10 raised to the power 7 into Z is what? Helium, right? So Z is what for helium? 2. So Z square becomes 4 into 1 upon N1 is what? 2. So N1 square will become 4 and 1 upon N2 square is what? 25. Okay. So 1 upon lambda will come out to be 1.09 into 10 raised to the power 7 into 4 into 25 minus 4, that is 21 divided by 25 into 4. Right, now this 4 and this 4 can get cancelled. Now we have to find out lambda basically, right? So lambda will be what? Lambda will be 25 divided by 1.09 into 10 raised to the power 7 into 21. You just have to reciprocate. By solving this particular thing, you will get that by solving this particular thing, you will get lambda in what? Meters, right? So to convert into what? Nanometer, you have to multiply it by 10 raised to the power 9. Multiply this answer by 10 raised to the power 9 to convert it into nanometer. So lambda, so if you will solve that particular thing, you will get lambda as 108.7 nanometer, right? So 1 nanometer is basically what? 10 raised to the power minus 9 meter. So 1 meter will be equal to what? 10 raised to the power 9 nanometer. That is why we were multiplying by 10 raised to the power 9. So conversions are very important from the examination point of view. Now coming on to the drawbacks of the Bohr's model. First drawback is that it is applicable for only one electron species, right? The species which are having more than one electron, it is not applicable to them. So if you take hydrogen, 1 electron, helium plus 1 electron, lithium 2 plus 1 electron, beryllium 3 plus 1 electron. So it is applicable to these species, but if you consider helium which has 2 electrons, it is not applicable to helium. If you take lithium, it is having 3 electrons, it is not applicable to lithium. If you are taking beryllium, it is having 4 electrons, it is not applicable to beryllium, right? So next is that he couldn't explain the fine spectrum of hydrogen when a powerful spectroscope is used. See, when a powerful spectroscope, first there was a modification in the instrument, a more resolution spectroscope was taken, right? So here it was seen that, let us say that this are the Lyman line, right? So along with the Lyman lines, many of the lines were also seen. So Bohr was not able to explain that why these extra lines are coming up. Okay, so these lines were very closely placed to the original lines that were being expected, right? So he could not account basically for these extra lines. Next was, he couldn't explain splitting of spectral lines into a group of finer lines under the influence of external magnetic field, that is Zeeman effect, or under the influence of external electric field, that is basically Stark effect, right? So let us say that this is a Lyman line, right? And when you applied magnetic field in it, let us say it is splitting into 3. Right, and similarly if you apply electric field on the Lyman line, it is also splitting into various lines, right? So if you apply magnetic field, it is known as Zeeman effect. If you apply external electric field, it is known as what? Stark effect, right? So he could not explain that why these lines were being splitted by the magnetic field and the external electric field. Next drawback was what? He couldn't give the theoretical reason for most of his assumptions. For example, he said that MVR, that is the angular momentum, is equal to NH by 2 pi. But from where this formula came, right? He could not explain that why the angular momentum was an integral multiple of basically H by 2 pi. Okay. Now, according to Bohr, the spectral studies of deuterium and hydrogen should be similar, but eventually when it was found out that deuterium was having a different spectrum that of hydrogen, so this was also not explained by Bohr's. Okay. See, next coming on to the Sommerfeld theory. Now this is very important. See, at each possible level, Sommerfeld explained that at each possible level there can be one or more elliptical paths along with circular orbit which are having slightly different energy level than the circular path. For example, Bohr explained that this is the orbit, right? This is the nucleus, let us say, and this is the orbit number 1. Now Sommerfeld said that this orbit is accompanied by elliptical paths also. Not circular paths but the elliptical paths. Can you see that this particular thing is a elliptical path that is associated with this particular orbit, right? So he said that one or more elliptical paths are associated with a orbit, and these elliptical paths are having different energy than that of the circular orbit. This is also important, right? So he said that angular momentum of these different paths are called as subshells. Okay, so orbit was explained by Bohr's, right? While Sommerfeld said that orbit were also containing subshells. Orbits were divided into subshells, which basically are the elliptical paths, were represented by azimuthal quantum number L. So Bohr gave what? The orbit number as N, that is the principal quantum number, and Sommerfeld gave the azimuthal quantum number, that is L, which is known as the basically subshell, right? So he said that the number of elliptical orbits can be given or can be valued by the value of L, right? So he said that the value of L, that is the azimuthal quantum number, or that is the basically number of the subshell, can be from 0 to n minus 1. Right. So for orbit number 1, L can have a value of 0 only. For orbit number 2, L can value as 0 and 1, because L is having a value of 0 to n minus 1. So 2 minus 1 will be 1. So it will have a value of 0 and 1. For n equals to 3, L can have a value of 0, 1 and 2, because 3 minus 1 is 2. And for n equals to 4, L can have a value of 0, 1, 2, 3, as 4 minus 1 is 3. Right. So basically he tell that n is the principal quantum number which basically gives the or signifies the energy of electron. Signifies the energy of electron, while L is the azimuthal quantum number which basically gives the angular momentum. It signifies the angular momentum. Okay. Yeah. So if L equals to 0, it is the S subshell. L equals to 1, it is the p subshell. L equals to 2, it is the d subshell. L equals to 3, it is named as f subshell. L equals to 4, it is named as g subshell, and L equals to 5, it is given as h subshell. Okay, so the value of L determines that what is the type of subshell, and each subshell is having a different shape, right? S, P, D, F, G, H are having different shapes, and also they are different in energies. Okay. So, in a given energy level, this we have already discussed, the number of possible subshells is 0 to n minus 1, right? Now, each energy level will have n subshells. This is also very important. See, when n was equal to 1, n can have only a 1 value. When n equals to 2, L can have 2 values. When n equals to 3, L can have 3 values. When n equals to 4, L can have 4 values. This means the number of elliptical orbits or number of subshells is equal to what? The orbit number. If it is orbit number 1, then 1 subshell, orbit number 2, then 2 subshells, orbit number 3, then 3 subshells, orbit number 4, 4 subshells. Okay. Now next we will move on to the explanation for splitting of spectral lines. Now Sommerfeld explained the splitting of spectral lines under high resolution spectrometer, that why those extra lines were being observed, right? So if you see, let us say that n equals to 2, L equals to what? 0 and 1. N equals to 1, L equals to what? 0. N equals to 3, L equals to what? 0, 1, 2. N equals to 4, L equals to what? 0, 1, 2, 3. Right? And N equals to 5, L equals to what? 0, 1, 2, 3, 4. Now we know that basically L equals to 0 is what? L equals to 0 is the S subshell. L equals to 1 is the P subshell. L equals to 2 is the D subshell. So, we can categorize as 1, 0 will make 1S because L equals to 0 is what? S. 2, 0 will make 2S. 2, 1 will make 2P. 3, 0 will make 3S. 3, 1 will make 3P. 3, 2 will make 3D. Okay, because we are considering L equals to 0, 1, 2, 3 as SPDF. Okay, and here if you see, it will be 4, 0, 4S, 4, 1, 4P, 4, 2, 4D, 4, 3, 4F. Here if you see, 5, 0, 5S, 5, 1, 5P, 5, 2, 5D, 5, 3, 5F. Okay, and so on. 5, 4 will be 5G. Okay, so now he said that, let us say Bohr was telling that if n equals to 2 and n equals to 1, there is a single line being observed, right? But according to Sommerfeld, this n equals to 2 will have what? 2s and 2p levels, right? So if the transition is taking from 2p, the line would be different of energy, and if the transition is taking from 2s, the line would be of different energy, means that there will be a slight energy difference because there are difference in the energy levels of 2s and 2p. Okay. So this was the basic difference between the Bohr's theory and the Sommerfeld theory. Sommerfeld theory was able to explain that why those extra lines were being coming, because the n equals to 2 was also associated with subshells of different energy, and transition from different subshells will lead to different spectral lines. Now, each of the subshells can further be divided into orbitals. See here that orbitals can be divided into what? Subshells. Now, orbit can be divided. Now, see here that orbit can be divided into subshells, and subshells can be divided into what? Orbitals, right? So, each of the subshells can further be divided into orbitals which have different orientation in space. That means that one will be present in the x direction, one will be present in the y, or one will be present in the z, right, based upon the type of orbital. Okay, but here comes the twist that all orbitals, let us say, of one subshell, if one subshell is having, for example, 3 orbitals, then these 3 orbitals will be degenerate. What does degenerate means? Degenerate means that they are equal in energy, right? When we were talking about orbit, one orbit if containing 3 subshells, they will have different energy. But one subshell if containing 3 orbitals, they will be same in energy. Okay. So let us see. So orbitals are explained by the magnetic quantum number, that is m or ml. Okay. So what are the possible values of m that can we have? Minus L to plus L. Okay. For example, if we take that L equals to 1, so m will have a value of minus 1, 0, plus 1. If we take L equals to 2 subshell, then m equals to minus 2, minus 1, 0, plus 1, plus 2. Right, and if L equals to 3, let us say, then m can have a value of minus 3, minus 2, minus 1, 0, plus 1, plus 2. Okay, so these are the possible values of m. Now, based upon the possible values, we can define that what are the number of orbitals that are associated in one subshell. Okay. So let us consider the S subshell, right? If you consider S subshell, for S subshell L equals to what? 0. So m will be equal to what? 0 only. That means only one value of m is possible and only one orbital of S is there. So if you write 1s, that will have only one orbital. If you write what? 2s, it will be consisting of only one orbital. If you are writing 3s, it will be consisting of only one orbital. Okay. Now coming on to the p subshell. For p, L value is equal to what? 1. Right. So m can have a value of what? Minus 1, 0 and plus 1. So there are 3 possible values for L equals to 1 subshell. Okay, that is the p subshell. So if you draw, let us say 2p subshell, then it will have what? 3 orbitals, right? Minus 1, 0, plus 1. If you consider 3p, it will also have 3 orbitals. Minus 1, 0, plus 1. If you have 4p, it will also consist of 3 orbitals, that is minus 1, 0, plus 1. Okay. Now considering the D subshell, D is what? L equals to 2. So the possible values of m are minus 2, minus 1, 0, plus 1 and plus 2. Okay, so what are the possible values? There are 5 possible values. So if you consider 3D, it will have 5 orbitals. 1, 2, 3, 4, 5. So this will be minus 2, minus 1, 0, plus 1 and plus 2. Okay. Similarly, if you are considering 4D, it will also have 5 orbitals named as minus 2, minus 1, 0, plus 1, plus 2. Similarly for 5D also. Okay. Considering the F subshell, if you take L equals to what? 3 for F subshell, right? So M will have a value of minus 3, minus 2, minus 1, 0, plus 1, plus 2. So it will having a plus 2 and plus 3. So it will be having how many values? 7 values. Okay. So if you draw 4F, let us say, it will have 7 orbitals. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, right? This will be named as minus 3, minus 2, minus 1, 0, plus 1, plus 2 and plus 3. Similarly for 5F also and 6F also. Now you must be wondering that why am I writing 4, 5, 6, right? I am writing 4, 5, 6 because these 1S, 2S, 3S or 2p, 4p. The numbers here are telling you about the orbits. These are what? The principal quantum number, that is what basically n. Okay, so here 1, 2, 3, 4, 5, 6 are what? The orbit number. 1 means orbit number 1 associated with the s subshell. Orbit number 2 associated with the s subshell. Orbit number 2 associated with the p subshell. Orbit number 4 associated with the p subshell. So that's all for today. We'll end up the session for now. Okay, thank you.